Next up is question 4. It says, find the sum of each series if it converges or show why it diverges. And part A, we're looking at the sum of -1 to the n times 5 over 4 to the n. And here the index n runs from 0 to infinity. So let's start by writing out the first few terms of the series. This is 5 minus 5/4 plus 5 over 4 squared minus 5 over 4 cubed, so on and so forth. And so we can see that this is a geometric series whose common ratio r is -1/4, right? Because if I multiply by -1/4, that's going to take me from term to term. And we note here that since common ratio r is strictly less than 1 in absolute value, this is a convergent geometric series. And the first term of the series, a, is 5, right? So to find the sum there, we're going to take the first term, a, which is 5, and divide that by 1 minus the common ratio, right? 1 minus r, which is -1/4. And that simplifies to 4. And so this is a convergent geometric series whose sum is equal to 4. All right. Part B, we've got -2/3 plus 2/3 cubed minus 2/3 to the 5th plus 2/3 to the 7th, so on and so forth. So here, notice we have a sign change, and this exponent is going up by 2 from term to term. So this is a geometric series with common ratio r, which is -2/3 squared here, right? So in other words, -4/9. The negative is needed to alternate the sign and the square because, again, the exponent's going up by 2 from term to term. And since r is strictly less than 1 in absolute value again, right, this is a convergent geometric series, and the first term, a, is -2/3. So to find its sum, we'll take a, which is -2/3, and divide that by 1 minus r, and that's going to be 1 minus -4/9. So this simplifies to -6/13. All right, moving on to part C, we're looking at the sum of 2 to the j plus 1 divided by 5 to the j, and then we're adding to that -1/3 to the j. Okay, so here j varies from 1 to infinity, so write out the first few terms. So we're going to get 2 squared over 5 to the first plus -1/3 to the first, and then 2 cubed over 5 squared plus -1/3 squared, so on and so forth. So what I'm going to do here is just break this up into two sums. Okay, so here in blue I have 2 squared over 5 to the first plus 2 cubed over 5 squared, so on and so forth. And then in red I have the -1/3 to the first, -1/3 squared, so on and so forth. Okay, so note here, just as a little aside, this is in essence really just the same thing as just distributing the sigma sign to each one of these summands, right? It's the same thing you do when computing an integral, right? You can distribute that integral symbol. That's really what we're doing here. And we'll talk about properties of summations a little bit later, but for now I just want to mention that's what really is going on. All right, so now each one of these sums, these are geometric series, right? So for blue, the common ratio r is 2/5, so this is a convergent geometric series. First term a is 4/5. For the second series here in red, r is -1/3, so again it's convergent. And the first term a there is -1/3. So what we're going to do here is just sum each individually and then combine the results. So for the blue series, we get a over 1 minus r, so 4/5 over 1 minus 2/5. And then for the red series, -1/3 over 1 minus -1/3. And that all simplifies to 13/12. All right, very good. So now let's go ahead and make a little space, and we'll look at the rest of these. Oops, sorry, that's not quite what I wanted. All right, there we go. 4D is next. So we're looking at the sum of e to the pi over pi to the e all raised to the nth power. And here n varies from 0 to infinity. So the first few terms are 1 plus e to the pi over pi to the e plus e to the pi over pi to the e quantity squared, so on and so forth. So this is a geometric series, and the common ratio r here is e to the pi over pi to the e. And now we note here that this common ratio is actually a number that's just a little bit over 1. Okay, e to the pi and pi to the e are actually pretty close to one another. They're like both around 22, 23-ish. And it's actually a fairly common Calc 1 problem to show that e to the pi is actually larger than pi to the e without a calculator, just using derivatives. Kind of a fun problem. But in any event, here, since the common ratio exceeds 1 here, right, so r is not strictly less than 1 in absolute value, in other words, is really what I'm getting at. The series diverges. That's it. All right, for part E, we got 1 point, and then there's 4 zeros and a 1, plus 1 point, again, 4 zeros and a 1, but now it's squared, and then here that number is cubed, so on and so forth. So this is a geometric series. Common ratio r is a number that's just slightly over 1, but still, again, the point there is that the common ratio r is not strictly less than 1. That's what we need for the series to converge, okay? And so here the series, again, diverges, all right? And then lastly, for 4f, it's basically the same thing here. Writing out the terms, we're going to look at 1 plus epsilon plus 1 plus epsilon quantity squared. This is, by the way, this E-looking symbol. This is a Greek letter epsilon. And so, yeah, this is a geometric series. Common ratio r is 1 plus epsilon, and we're told in the problem that epsilon is a strictly positive number, right? So 1 plus epsilon, well, it's going to be some number larger than 1. And again, in order for a geometric series to converge, we need r to be strictly less than 1 in absolute value. And so this series will diverge. Okay, well, that's going to do it. In the next video, we'll look at question 5, which is just a few more examples working with geometric series. All right, thanks so much.